Dear audience, good day and thank you for listening to this poster presentation. My name is Anatoly Parahovnik and I am a PhD student at the University of Central Florida under the supervision of Dr. Yoav Peles. In this short video, I will walk you through my poster titled Subcooled Flow Boiling of Carbon Dioxide Near the Critical Point inside a Microchannel. The work was recently published in the latest volume of Physical Review Applied. It is the first paper in the reference list of this poster. The thermophysical properties of fluid near the critical conditions are unique. For example, the density of a fluid transforming from vapor state to supercritical state will increase abruptly. For fluid transforming from liquid to supercritical, the viscosity will drop, and the specific heat will always spike around the critical condition. These distinct features of critical carbon dioxide can be leveraged to enable cooling of high-power electronics. A microfluidic device with a plain microchannel of hydraulic diameter of 0.3 mm was designed, built, and used to perform experimental study of CO2. The microfluidic device had an embedded heater and 4 temperature sensors, which can be seen here in B, and was made of fused silica to allow optical access and low heat losses. The device was placed in an open-loop type experimental setup that enabled fine control of pressure, mass flux, and temperature near the critical point. It was found that the onset of nucleate boiling occurred at low superheat temperature that ranged from 1.6 Kelvin at reduced pressure of 0.81 to 0.3 Kelvin at reduced pressure of 0.95. The onset of nucleate boiling was dependent on the working fluid and invariant to mass flux and gravity. The measured heat transfer coefficient ranged from about 50 to about 200 kW per meter square Kelvin for reduced pressures of 0.81 and 0.95 respectively. The heat transfer coefficient was dependent on the operational pressure and heat flux, but invariant to mass flux and gravity. The experimental results was compared to several established flow boiling correlations. Schacht's and Kandilkar equations, which are suitable for subcooled flow boiling of different fluids, were found to underpredict the experimental results. A specific Chang's correlation, developed for boiling of near-critical CO2, presented a better prediction of the experimental results. Nevertheless, the equation underpredicted the measured values for reduced pressure above 0.87, which were outside the correlation range. Finally, I would like to express our deepest gratitude to Dr. Mark Spector from the Office of Naval Research and the Israeli Ministry of Defense for funding this work, and to the Cornell University microfabrication facility that enabled us to fabricate a microfluidic device. And thank you for listening to this walkthrough, and I would be happy to have follow-up discussion if you have any other questions. Thank you, have a nice day.